the recording. And Annika, the floor is yours.
Yeah, thank you for the kind introduction and for the invitation to speak here in this online seminar series. So with my group, I work on transport theory in solids. And when I say transport, you usually think about a charge current, which is carried by electrons. But I mean, this is an Orbitronics seminar, so we know electrons do not only carry charge, they also carry spin and an orbital angular momentum. And our interest is in describing transport of spin and also of orbital angular momentum. So in this example, which I sketched here, we have a non-magnetic metal. We have equal number of spin up and spin down states. And if we drive a charge current in this material, then we do not transport any spin, but we do transport only charge. It's different if you consider a ferromagnet. So here you have an imbalance of spin up and spin down states. So if you drive a charge current in this material, you also generate a spin polarized current. However, we are interested in generating spin transport without using any ferromagnets. And this is also possible, as you probably know. So in this example, we have a non-magnetic metal. We drive a charge current through the material. And in addition, we generate a transversal pure spin current. And the simple picture for that is that electrons with opposite spin move in opposite transversal directions. So this means we generate a pure transversal spin current. There is no charge transport. The electrons move in opposite directions, but there's a finite spin transport or spin current. And if we want to generate such spin currents in non-magnetic materials, then usually we need spin-orbit coupling, which can be considered like a correction term to the Hamiltonian. And this spin-orbit coupling term is quite important for spin transport phenomena. Usually we need heavy elements providing large spin-orbit coupling, and their disadvantage is they are usually rare, expensive, or toxic, which is not so ideal for potential applications. However, the electrons also carry this orbital angular momentum. And therefore, the question or the idea is, can we also transport this orbital degree of freedom? Can we generate something like an orbital current? The big advantage would be that for orbital transport phenomena, we would not need any spin-orbit coupling. So in general, we might consider also light elements which are better available and cheaper. So this might help us to realize more sustainable electronics. So the question is now, how can we generate spin currents, orbital currents? How can we generate spin and orbital polarizations? And we are working on this second question, how can we generate spin or orbital polarization in non-magnetic materials? And in the recent years, we have intensely been working on one effect called the Edelstein effect, and this is also the main topic of this talk. So here I would like to briefly introduce what the Edelstein effect is. It's basically very simple. You apply a charge current or an electric field to a system with broken inversion symmetry, for example, to such a surface. And even if the system has no net magnetization, this electric field can generate a finite spin density. So your sample might become magnetic. And this is the so-called Edelstein effect. You need spin-orbit coupling to get this spin polarization. And we also call that a charge-to-spin conversion. However, what can we do now with the spin polarization? So the idea is now you might have a ferromagnet on top, and then your generated spin polarization acts a torque onto the magnetization and might switch that magnetization. So you could use the Edelstein effect for electrical magnetization switching without need of any magnetic fields. And this could be useful for non-volatile information storage. However, as I said, there's also the orbital degree of freedom. So you can think about an orbital analog of the Edelstein effect, which we call the orbital Edelstein effect. Originally, it has been discussed just for spin, but in recent years, and actually already in the 80s, the orbital Edelstein effect has been predicted and discussed. So the effect is very similar. You apply an electric field, you generate a finite orbital polarization. I think the more general definition of the Edelstein effect would be we have a current-induced magnetization, which has spin as well as orbital contribution. So usually they coexist. And now the nice advantage of this orbital Edelstein effect is you do not need any spin-orbit coupling. And in many materials, the current-induced orbital magnetization is much larger than the current-induced spin magnetization. There's also a third Edelstein effect, the so-called inverse Edelstein effect, which is the reciprocal of the direct Edelstein effect. Here you inject a spin current into your system, for example, into this interface, and this is then converted into a pure charge current, which can be detected quite easily experimentally. And since the direct and the inverse Edelstein effect are reciprocal, we can also compare the corresponding conversion efficiencies, at least qualitatively, which will be important later in this talk. So in this talk, I'm planning to provide you some introduction into the theory we are using, which will help us to better understand the existence of the Edelstein effect. And then I will introduce two material classes which are very promising for the realization of the Edelstein effect, namely oxide-based two-dimensional electron gas, so interfaces between oxides. And I will also talk about the Edelstein effect in a bulk material in a ferroelectric semiconductor germanium telluride. But before we can consider materials, we need an appropriate theory to describe our transport. And in this talk, I will talk about only semi-classical transport theory, namely Boltzmann transport, which is very simple, but also quite insightful. So you can learn a lot from using Boltzmann transport theory. The main idea is we construct wave packets out of Bloch states. These wave packets have a finite width, which is large compared to the lattice constant, but small compared to the length scale of external electric or magnetic fields. So this really corresponds to a particle-like picture, which you know from classical physics. And now we can consider one wave packet, and we can calculate how the central coordinates of this wave packet evolve if we apply external fields. And for the change of k, or the time derivative of k, we get a force, which is actually the Lorentz force by the electric and magnetic fields. And this is equivalent to the classical equation of motion for an electron in electric and magnetic fields. And for r dot, the velocity, we get the group velocity, which is just the k derivative of the band structure, and an additional anomalous velocity term, which comes from the Berry curvature of the system. And now we want to calculate transport, and for that, we need to know the distribution of states. We need to know how these states are occupied. And this we usually describe by the so-called distribution function f, which tells us if a state is occupied, then it's 1, or if it's not occupied, then it's 0. And we start with 0 temperature, and then we know that all the states below the Fermi level are occupied and the states above are not occupied. So here our equilibrium distribution function is the Fermi-Dirac distribution function. Now we want to know how the distribution function behaves if we apply external fields or temperature gradients. And this can be described by the semi-classical Boltzmann equation. So this Boltzmann equation contains a diffusion term accounting for spatial inhomogeneities, a field term, and a scattering term. And in the following, I will assume the system to be stationary and spatially homogeneous, which means that only the field term and the scattering term survive. And for the scattering term, we do some quite simple approximation. We say we have a characteristic relaxation time, tau, and the scattering term depends on the deviation of the distribution function from its equilibrium. And with this ansatz, and using the semi-classical equation of motion, we can now solve the Boltzmann equation and we get a solution for our distribution function. Namely, it consists of the equilibrium distribution function and a term which scales linearly with the applied electric field, with the group velocity, relaxation time, and the energy derivative of the equilibrium distribution function. So now let's look at our band structure with our occupation of states. We apply an electric field, and this means we have to look at the energy derivative of the distribution function, which is non-zero only around the Fermi level. So actually it means that the occupation of states changes around the Fermi level. The sketch here is not completely true, so it's not really a shift of all the states. It's more that we get more states here and less states here. So now we know how the distribution of the states behaves under the influence of external fields. And now we want to calculate macroscopic properties like a charge current. The charge current is the sum over the velocity of all occupied states. The spin density would be the sum over their k-dependent spin expectation values. And I would like to illustrate what this means for the charge current. So here we see the Fermi surface of a free electron system. So it's just a sphere. In equilibrium, we have equal number of electrons moving to the left and to the right. So there would be no net charge current. But now we apply an electric field. This leads to a reoccupation of states. We have more states occupied here and here, meaning that we have more states moving to the left and to the right. And this gives us a finite charge current in the direction of the electric field. And this reoccupation of states is often illustrated like here, like a shift of the whole Fermi sphere. But we should keep in mind that actually only the states at or around the Fermi level are really contributing to transport. And with this background knowledge, we can now move directly towards the Edelstein effect. The Edelstein effect has first been discussed in so-called Rashba systems, which can occur at surfaces or interfaces. So here is the example of a metal surface, and we consider now a two-dimensional electron gas living at the surface. And the simplest approximation for that is, of course, a free electron system. So we have a parabolic band structure, which is twofold spin degenerate. However, at our surface, inversion symmetry is broken. So above the surface, we have vacuum, and below we have some material. So the structure already breaks inversion symmetry. And this means we have a potential gradient in the direction of the surface normal. And this potential gradient, together with spin-orbit coupling, leads to the emergence of an additional term in the Hamiltonian, which we call the Rashba spin-orbit coupling term. So this term is characterized by the parameter alpha. And then the characteristic form of this Rashba term is kx sigma y minus ky sigma x. So this is something like a cross product, k cross sigma times surface normal. And this term now leads to a splitting of our free electron parabola into two parabolas with opposite spin polarization. And this is the famous Rashba effect. Importantly, the splitting is proportional to this Rashba parameter, which is also a measure of the spin-orbit coupling strength. And our system is two-dimensional, so I should also sketch a two-dimensional band dispersion. And here we immediately see that our isoenergy lines are two concentric circles. And now we can calculate the spin expectation value for each point. And we find that each spin is compensated by an opposite partner. So there is no net magnetization in the system. Now we apply an electric field. This leads again to a reoccupation of states. We have no more states occupied here than here. And this means we generate a finite spin density perpendicular to our electric field in the plane of our two-dimensional electron gases. And this is the Edelstein effect. Importantly, the contribution from the outer and the inner Fermi circle partially compensate because they have opposite spin expectation values, but this compensation is only partially. The outer circle is much larger, or it's larger than the inner one. So something finite survives. And one can also calculate that for such a Rashba system, and one finds that the spin density is basically constant if you are in this energy range above this crossing point. And the spin density scales with a delta K, which also scales with alpha. So you can say the larger my spin splitting, the larger the Edelstein effect is. And here I just summarized some literature values for this Rashba parameter for some standard systems like the silver surface, the gold surface, and also the silver bismuth surface alloy. And you see we have here like 2 orders of magnitude in between these systems. These are just typical values which exist in nature. So this is the Edelstein effect, which has been originally discussed in these two publications. However, we know that there are also orbital expectation values. We can have systems with orbital textures. So just imagine a system which has an orbital texture like that. We apply an electric field, and this would also induce finite orbital density in our system. So the full Edelstein effect would be that we induce a magnetization in our sample, and this magnetization has spin as well as orbital contributions. They usually coexist, so this is not supposed to be like a pattern. It's really homogeneously distributed over the sample. And usually the orbital contribution to the magnetization is much larger than the spin contribution. Yeah, and after this general introduction about Rashba systems, I will move towards more realistic materials, and I will start with a material class which provides a realization of Rashba two-dimensional electron gases, namely oxide interfaces. And this is work which has been done together with Børge Göbel and Ingrid Mertig from Halle University, and with our experimental collaborators, the group of Manuel Ibis. Yeah, so these oxide systems usually consist of two perovskite oxides which are insulating. You put them on top of each other and you generate a two-dimensional electron gas at the interface. The material or the system I will talk about is a bit different. So we have strontium titanate, which is a perovskite insulator. And then you can put aluminum oxide on top, which is also insulating. And then you also generate a two-dimensional electron gas at this interface, which is conducting, which has very interesting properties like high mobilities. It might even be superconducting. So it's a very interesting system to study. On top of that, if you look at the structure, you see already that inversion symmetry is broken at this interface. We have STO here and we have aluminum oxide here. So there's definitely no inversion symmetry. And therefore, we expect some Edelstein properties at this interface. We used an effective tight binding model Hamiltonian to simulate the band structure at this interface, and I will now comment on this band structure a little bit. So we know that these are the T to G orbitals, which are relevant for the formation of the two-dimensional electron gas. I will now start constructing this Hamiltonian. So the simplest approximation is that we just use parabolic bands for our ZX, YZ, and YX orbitals. And then, of course, we get parabolic energy dispersion. However, as I said, inversion symmetry is broken. And if we now look at the orbitals, the broken inversion symmetry allows us to consider some hopping terms in the Hamiltonian, which are usually forbidden by inversion symmetry. But since inversion symmetry is broken here, these terms are allowed. If you have a look at these terms, then you can write them this way. So you have a term sine kx times Ly minus sine ky times Lx. L is the orbital angular momentum operator. If you now think back to the expression for the Rashba effect, this term looks very similar to the Rashba term. The main difference is that we don't have the spin operator here, but the orbital operator. So we can call that an orbital Rashba term. We have sine instead of kx here, and this is only because now we have a lattice periodic model. So this is like an orbital analog of the Rashba effect, which exists in this interface. And you can see it leads to a hybridization between the bands, but still each band is twofold spin degenerate because we have not included the spin-orbit coupling yet. So let's switch on spin-orbit coupling. This is just the L dot S term. And now the spin-orbit coupling leads to spin splitting of the bands, which you can see nicely here. And if you zoom into the region around the band edges, you would see something like a Rashba splitting. However, the splitting is rather small, so you don't see it in the full band structure, but actually each point except of gamma is spin split. So if you look at the band structure, you can estimate a value for the effective Rashba parameter, which is in this order of magnitude. So it's 10 millielectron volts. If you look into the table I showed in the previous slide, this is comparable to silver, so not very large, but there is an effect. And this Rashba splitting now motivated experimentalists to study the Edelstein effect in these oxide heater structures. And before I comment on that, I will just also show an overview on the spin and orbital textures. So I will show some figures here now. I will lift the energy of our system. And in these figures, we see on the left-hand side the spin texture of the outer band, and on the right-hand side, spin texture of the inner band. So remember that each point here actually consists of 2 points, which are only slightly split. Oh, sorry. Yeah. And if we look at these textures, they look very much like a Rashba system. So the spin expectation value is perpendicular to K. And the two bands have opposite spin expectation values. So we can really say we have a Rashba-like band structure. Now we can also look at the orbital textures. And here we calculated the orbital textures using the atom-centered approximation, which means that we evaluate the orbital angular momentum around in the vicinity of a single atom. So that's only local contributions to the orbital angular momentum. We have dxy, dyz, and dxz orbitals, and they hybridize, and this gives us some finite orbital expectation values. And these orbital textures look very similar to the rush bar spin texture, so they are also perpendicular to K. But if you compare now the two bands, you see that on the outer band we have slightly larger orbital expectation values than on the inner band, and this will be important later on. But still we call it a rush bar-like orbital texture. Now we increase energy. The second band is occupied. This is also has a very similar rush bar texture. At higher energies, the system is not so, the bands are not so isotropic anymore. So we have hybridization in between different bands and our Fermi surfaces become anisotropic. And then if we are slightly below the Fermi level, something interesting happens, namely, I mean, the Fermi surface is now very different from circles, so that's definitely not rush bar-like anymore, but still we have perpendicular spin momentum locking, so the spin is more or less perpendicular to K. But if we now zoom into a tiny region here, then we see that there are 4 bands coming very close to each other. So we have an avoided crossing here. And now we see that the spin texture is strongly modified. So we have large spins at the outer band and rather small spins at the inner one. This will also become important later on when we discuss the Edelstein effect. Yeah, so as I said, the rush bar features motivated experimentalists to study spin charge interconversion in these systems. And our collaborators, the group of Manuel Bibes, they did not measure the direct Edelstein effect, but the inverse spin Edelstein effect. So they did a spin pumping experiment to inject a spin current into the 2-dimensional electron gas here between STO and aluminum oxide. And then they measured the charge current, which is induced by the inverse Edelstein effect. And this conversion is characterized by a quantity lambda. And this quantity tells you how much charge current is generated if you inject a spin current. In addition, they apply a gate voltage. By this gate voltage, they can modify the charge carrier density of the system. And if they apply that gate voltage, they see that either the charge current can be modified, also the order of magnitude of the induced charge current is changing, so you can reach a maximum. You can even change the sign of the charge current. So this curve here of this conversion efficiency shows a very unconventional behavior with many extrema and sign changes. And this is something which is not expected for pure rush bar systems. So if you just have a rush bar model, you would expect something rather constant. To understand what's happening here, we used our tight binding Hamiltonian and calculated the Edelstein effect. And since the inverse and the direct Edelstein effect are reciprocal, we can then compare the corresponding spin to charge and charge to spin conversion efficiencies qualitatively. So for the direct Edelstein effect, we use a quantity which we call Edelstein susceptibility. This tells you how much magnetization or magnetic moment is generated by applying an electric field. And how we can compare these curves qualitatively. In our simulations, we simulated this modified charge carrier density just by a rigid band shift. So we just shifted our Fermi level, which is a rough approximation, but it's reasonable for this purpose. And we see that our theoretical calculations reproduce the experiment quite well. So we can reproduce these extrema and even the sign changes. But to really understand what's happening, we did a band resolve calculation. So in this plot, we see now the contributions of each individual band to the total Edelstein effect. And I will now guide you through this plot. So we are now at the band edge. So whenever a new band pair is occupied, we have rush bar-like band structure close to the band edge and also rush bar-like spin textures. So this gives you, whenever a new band pair is occupied, an additional positive contribution to the Edelstein effect, like here and here. And this explains this step and also this sign change. In the orange band pair, we have opposite spin texture, and therefore it gives you an opposite or a negative spin Edelstein effect, which explains this sign change here, or this maximum here. And then at higher energies, band hybridize, so it's even more complicated, but I would like to comment on the energy slightly below the Fermi level, where we had these 4 bands coming close to each other, which modified our spin texture. So we have large spins at the outer band and only small spins at the inner one, meaning that a large Edelstein contribution from the outer band is only weakly compensated by the inner band. And weak compensation means enhanced Edelstein effect. This can lead to this pronounced extremum here. By this band-resolved analysis, we could understand the experimentally observed curve qualitatively and could understand why they observe such a strange or unconventional behavior. So the observation of the direct Edelstein effect, which we think of in a very simple view, is just we have our heterostructure, we apply an electric field, and we induce an interfacial magnetization or spin density. So far I just discussed spin density, but we know that our system also has orbital expectation values in K-space, so there should be an orbital Edelstein effect. And this is what we calculate here. So maybe we focus on this curve. We see in blue now the orbital Edelstein effect, and you directly see it's much larger than the spin Edelstein effect. So our experiment or our setup would be we generate an interfacial magnetization, but this is dominated by the orbital Edelstein effect, and you see the orbital effect even has a usually opposite sign than the spin Edelstein effect. Why is the orbital Edelstein effect now so large? So let's look at the corresponding spin and orbital textures. Close to the band edges, both of them are Rashband-like. But as I said before, for the spin, we have more or less equal length of all the expectation values. But for the orbital moment, we have rather large moments at the outer circle and only small ones at the inner one. If we now apply an electric field, we get some contribution from the outer band to the spin Edelstein effect, which is then directly compensated by the inner band, so only a small Edelstein effect from the spin moments survives. From the orbital moments, we get a large contribution from the outer band and only a very small opposite contribution from the inner one. And here we have again reduced compensation, which means enhanced effect. This explains, at least qualitatively, why the orbital Edelstein effect is so large here. So on the previous slide, I showed you the nice agreement between theory and I showed you the nice agreement between experiment and theory, just considering the spin Edelstein effect. On the other hand, I just told you that the orbital Edelstein effect should be dominant. So let's look at the experiment again. In the experiment, they do spin pumping, which means they have a ferromagnet and they inject a spin current from the ferromagnet into this interface. And therefore, we think what they observe is really the inverse spin Edelstein effect, which happens here at the interface, and this inverse spin Edelstein effect then needs to be compared to the direct spin Edelstein effect. However, if you are able to do an experiment like that, and if you are able to measure the interfacial magnetization, then this should contain also a very dominant orbital contribution. However, like 2 years after our prediction of this orbital Edelstein effect, there has been some experimental observation in a similar experiment. So it was also a spin pumping experiment, or I should better say angular momentum pumping experiment. And they also injected a spin current via the Seebeck effect or inverse Seebeck effect. And here is also a gate voltage dependence curve of this conversion efficiency of the inverse Edelstein effect. And in this paper, they did some analysis with respect to the orientation of the system and compared that to theoretical calculations. And they found that the signal which they observe consists of spin and orbital contributions, and that the current which they inject, I think in this experiment, is like 94% of spin current and 6% of orbital current. So the if this current is then converted into a charge current, it contains contributions from the inverse spin as well as inverse orbital Edelstein effect. So STO is a very popular system of these oxide interfaces. And we were looking also into other systems. So we were also focusing on potassium tantalate with the idea that we are looking for systems with large spin-orbit coupling. And we were hoping that the large spin-orbit coupling from tantalum would increase our Edelstein effects. So here's some ARPIS data also measured by the group of Manuel Bibers, on a potassium tantalate-based two-dimensional electron gas. And what is nice about the system that you have really a huge Rashba splitting, which is even visible in outputs. You can see it here. So we did our tight binding fit to this system, and you see that most bands have also a small Rashba splitting, but the orange band pair has huge Rashba splitting. So we even estimated this Rashba parameter, which has this value. And now look at our table again. This is comparable to gold and 1 order of magnitude larger than an STO. And as I said in the beginning, the spin-Edelstein effect is expected to be proportional to this delta K splitting and also to be proportional to this Rashba splitting. Therefore, we expected a huge Edelstein effect in the system, and we were very motivated to calculate that. And this is now the result of our calculation. So on the top panel, you see the spin-Edelstein effect with the red curve. And if we now compare absolute numbers, that's comparable to STO. So it's a sizable effect, but it's not as huge as we were hoping. If you now look at the orange band, I mean, there is some effect, but it's definitely not as huge as we expected, given that we have such a huge Rashba parameter here. So the question is, why is the effect so small? We can also look into the orbital Edelstein effect. Again, this is comparable to STO. And again, the contribution from the orange band pair is not as large as we were hoping. So to understand that, we looked again at the textures. So this figure is now even a bit more complicated to read. In the top panels, you see the spin expectation values. In the bottom panels, the orbital expectation values. And on the left, you see the values at the outer bands. On the right, it's for the inner bands. And now we are quite low in energy. We have Rashba-like band structure and also Rashba-like spin and orbital textures. This gives us, as expected, some small contributions to the spin and the orbital Edelstein effect. Now we go higher in energy, and now the orange band pair is occupied. You directly see the huge splitting delta K, but you should also immediately see that the spin and orbital expectation values are very small. So the orbital expectation values, they are still Rashba-like, but they are much smaller than at the other bands. And now we zoom into this plot, and we see that the spin expectation values are even not Rashba-like anymore. So they are definitely not perpendicular to K. They are somehow rotating if you move along the line. So that's not really a Rashba-like system anymore. So what happened? To understand that, we projected the Hamiltonian onto the two orange bands. And this is what we got as an effective Hamiltonian. So the important term is that term. This looks like a Rashba term, but we have a matrix here, tau. If this was the spin, then it would be a Rashba system. But our tau is unfortunately not the spin, but just the pseudo-spin. And this pseudo-spin is more or less the difference of the spin operators of the two orbitals, zx and yz. And if we want to calculate the spin expectation value, we need to look at more or less their sum. And since our bands consist of 50% zx and 50% yz orbitals, their spin expectation values kind of compensate, and therefore we expect almost no spin expectation values here. So the problem is this 50-50 superposition of the states, which gives us these small spin expectation values. And we thought about what to do to resolve that problem. And we had the idea to induce some anisotropy to our system. So in another model, we just induced some asymmetric on-site potential between the zx and the yz orbitals. And now our states are not 50-50 anymore. It's like 62-35. And if you now look at the spin textures, you see that they are already enhanced. So we can enhance our spin expectation values. Also, the orbital expectation values are slightly enhanced. And now we can look at the spin Edelstein curves again, and we just focus on the orange plot. You see that the contribution from the orange band is now already enhanced by a factor of 2 compared to the original model. Unfortunately, all the other bands are also affected by this asymmetry, so the total Edelstein effect, which is the superposition of these bands, is even reduced. But the purpose of this modeling was only to show that by inducing this asymmetry, we can enhance the contribution from this orange band. Now let's also look at the orbital contribution. if we induce this asymmetry, the orbital contribution from the orange band pair is only slightly enhanced, and also the total Edelstein effect is not really changed. It's a little bit decreased. And if you now look at the textures again, you see that this asymmetry did not have such a big influence on the magnitude of the orbital effect. So it seems that the orbital Edelstein effect is more stable against external perturbations like inducing asymmetry. So originally, this Edelstein effect has been predicted for two-dimensional electron gases at surfaces or interfaces, but there is no reason that there is no Edelstein effect in bulk materials. So there have been predictions for bulk crystals which have broken inversion symmetry in their lattice structure. And one of these materials, which is quite interesting from an Edelstein perspective, is germanium telluride. This is a ferroelectric semiconductor which exhibits a bulk Rashba effect. And this is our recent project, which has been done by Sergio Leiva at Halle University. And we collaborated with our partners from Grenoble, and the DFT calculations were done by Libor Wojacek. So germanium telluride has a rhombohedral structure, and now we see in blue the tellurium atom sitting at the corners. And in the center, there is germanium, but it's not exactly at the center. It's a little bit displaced along the 1-1 direction. And this polar displacement gives rise to a finite polarization of the system. And this breaks inversion symmetry. And whenever there's inversion symmetry broken, we should think about the Edelstein effect. So these are bond structure calculations performed by Libor. And in black, we see the band structure without spin-orbit coupling. And in red, we see now the influence of spin-orbit coupling. And of course, this is much more complicated in the simple models we used before. But I will focus only on some points of the band structure. So I will focus on the region around the L point, which is here in the Brion zone, and the Z point, which is here. So we zoom into these points. And now we see that we have in the valence band some Rashba-like splitting. This most pronounced around the Z point. So here we see now the band structure in the plane containing the Z point and in the plane containing the L point. And we call that a Rashba-like band structure because it's very similar to the Rashba model I showed at the beginning. And now we can look at our unit cell again and rotate this a bit. So we have now our polar axis. And this is now a very similar situation to our Rashba surface I discussed at the beginning. So on the Rashba surface, we had this potential gradient pointing in one direction, and now we have this polarization axis taking over the role of this potential gradient. So that's like a qualitative explanation of this Rashba-like picture for germanium telluride. And now it's even possible to derive an effective Hamiltonian describing the band structure in the plane containing Z. And this effective Hamiltonian has just some parabolic contribution, and then a term which is actually the Rashba spin-orbit coupling term. So this is a Rashba term in the plane. And then we get an additional term, which is also known as Rashba warping term, or simply warping term. This term arises because we don't have a perfectly rotational symmetric system anymore. So it's a system with C3V symmetry. So we have only 3-fold rotational symmetry. And remember, in the Rashba system, it was like isotropic. And this warping term also leads to the effect that the ZU direction is different than the ZA direction. However, using this model, we can now get a rough estimation about the effective alpha Rashba parameter, which is now 5 electron volts angstrom. So this is again 1 order of magnitude larger than KTO. It's compared to the silver bismuth surface alloy. So we can say this is really a huge Rashba splitting, which makes these materials, or this material, very promising from the Edelstein perspective. However, we should always keep in mind that this band structure only describes the states in this plane. And now we have a 3-dimensional material, so our band structure is much more complicated, and we have many more states contributing to the Edelstein effect. And therefore, we visualize here the isoenergy surfaces at one distinct energy. So usually the system is p-doped, so we are in the valence band. And we see now all the sheets of the Fermi surface. In the top panels, you see the orbital expectation values at the ISO energy lines. And here you see the spin expectation values. For the spin, it's quite simple. We have 0.5 h bar almost everywhere with slight deviations, but the orbital texture is very interesting. So we have some hotspots where we have super huge orbital expectation values. Here I have to say we calculated the orbital expectations values using the modern theory of orbital magnetization, which contains local as well as itinerant contributions. And whenever you have many bands coming close to each other, then you can get very large values for these orbital magnetic moments. Just for visualization, we also plot here the orbital and spin expectation values in this Z-plane, where we have very nice star-like Fermi lines, which is the typical picture you get if you have a rush bar effect with warping. And as before, you see the nice spin momentum and orbital momentum locking. So you usually have spin and orbital expectation values perpendicular to K. In addition, you have some out-of-plane contributions, which are shown in blue here. This is just a consequence of this warping term. So due to these nice spin and orbital textures, we calculated the orbital and the spin Edelstein effect in the bulk crystal. So the picture is now you apply an electric field and you induce a magnetization or a magnetic moment in the bulk of the system, not only at the surface. And again, I show in this plot the Edelstein conversion efficiency, this chi, which tells you how much magnetization you generate if you apply an electric field. And for comparison, we also show the band structure here. And in color, we see on top of the band structure now the orbital expectation values and the spin expectation values. And you see we have a complicated band structure, and therefore also the signal is not so easy to analyze. But I would only like to mention that for the orbital Edelstein effect, we get one pronounced extremum slightly below the band edges. And for the spin Edelstein effect, we get even some sign changes. And most importantly, the orbital contribution is enhanced by an order of magnitude by a factor of 10 compared to the spin Edelstein effect. And to understand this extremum, we can have a look at the orbital textures. So close to these band edges or band crossings, we have rather hotspots of orbital expectation value, which should increase our orbital Edelstein effect. On the other hand, our density of states is decreasing if we approach the band edge. So we have two competing effects, and this leads to pronounced maximum. This maximum is not related to any particular point of the band structure. It's more a consequence of decreasing density of states and increasing orbital moment if we approach the band edge. And maybe one last comment, which makes these ferroelectric semiconductors so interesting. You can switch the polarization direction if you apply an electric field. And if you switch that polarization direction, then spin and orbital textures would also be inverted and the band structure would remain the same. So by polarization switching, you should be able to switch the orientation of the spin and orbital Edelstein effect. So this, and finally, we were interested in the question, what is the role of spin-orbit coupling? So you know for spin Edelstein effect, you need spin-orbit coupling. If you switch that off, you have no effect anymore. But we know that orbital transport can exist without spin-orbit coupling. And in our model, of course, we can switch off spin-orbit coupling. Here we see now the orbital textures, which are actually very similar to the orbital textures with spin-orbit coupling. And we also calculated the orbital Edelstein effect with and without spin-orbit coupling. And you see these curves are very similar, and this has been also predicted for many other materials, that for the orbital Edelstein effect, there is no much influence of spin-orbit coupling on the final result. And this finally brings me now to the end of my talk. So I introduced the Edelstein effect, which is a current-induced magnetization in systems without inversion symmetry. And then I introduced two prominent material classes, oxide interfaces, where the main conclusion was that orbital magnetization is larger than spin magnetization, and this general approximation that the effect should increase with the spin splitting is not always sufficient. It's more complicated. And then I introduced also bulk rushbar semiconductors, which can also have large Edelstein contributions. And again, orbital contribution is much larger than spin contributions. Finally, I would like to mention my group members from MPI Halle, Dirk Farmer and Ricardo Sousa, and also Sergio Leva from Halle University, who did the work on the germanium telluride. And I would like to mention our collaborators from Laboratoire Albert Ferl in Palaiseau and also from Grenoble University. And finally, I would like to acknowledge our funding, and I would like to mention the recently started Excellence Cluster Center for Chiral Electronics, which is a collaboration of 3 German universities, Halle, Regensburg, and Berlin. And we are currently hiring many PhD and postdocs. So if you're looking for a PhD or postdoc in the field of chiral electronics, which is also interesting from an orbitronic perspective, then check out our webpage. This brings me to the end of my talk. Thank you for your attention.
Well, thank you very much, Annika, for this very pedagogical, very clear, and quite impressive work. Do we have any questions in the audience? So you can either speak up or drop a message in the chat box. So I'll wait for 1 minute, and otherwise I will start with my own questions. Yeah, Cyril.
One comment and questions. Thank you for this very pedagogical presentation. It was very nice. I have your interpretation about the fact that orbital contribution is larger than spin is because the two, like say, circle, they have different amplitude. This is compared to the spin. But I have noticed in the calculation that we did that, in fact, sometimes, well, for the spin, it's always opposite, while sometimes for orbit, they are in the same direction. So this is, I think, also some kind of origin of the orbital contribution. And so because you didn't show that, but did you notice this in your calculation or?
Yes, so we also noticed that. So in these oxide interfaces, we once did like a test calculation where we first switched off spin-orbit coupling and then switched on tiny values of spin-orbit coupling. And if you have very small spin-orbit coupling, then often the orbital moments of neighboring bands are still parallel, I think.
Yes, yeah, this
and
is
then
what
at some point they are switched. That's true. Yeah, that's an important point. Yeah.
Okay, and my other, well, it's not a question; it's kind of a comment. Also, all these systems, they are, well, the calculations are done in perfect system. What about defects, and how much does it affect this physics? Do you have an idea, or does it spin more or orbital more affected, or the same? Do you have an idea of that?
So the only unperfectness we include is only scattering at impurities, but we still use the perfect ground state band structure to calculate. That's true. So we have not really included disorder. From my experience, whatever I observed in calculations, whenever I added a perturbation to the system, like anisotropy or magnetic fields, then usually the orbital contribution was more robust than the spin contribution. But I'm not sure if this can really be transferred to unperfect systems. That's only what I observed for perturbations to the perfect system.
Okay, thank you.
Thank you, Cyril. So we have a couple of online, of questions in the chat. So the first one is from Suryakanta Mondal. Is the current due to the Edelstein effect reciprocal? Could you perhaps, Suryakanta Mondal, if you're online, can you please specify your question? I'm not sure I understand it. Okay, so no reactions.
So maybe I can comment on that. So all the calculations I've shown are in linear response. And there, I would say all the calculations are reciprocal. So if it means if you invert the electric field, then the effect would also be inverted. But there are also very interesting non-reciprocal effects related to Edelstein effect. So if you go beyond linear response, then you can have higher order contributions, which then of course would be non-reciprocal. I don't know if this was the idea of the question. But what I showed here is just linear response.
Thank you very much. So we have another question from Abhijit Calais. Nice presentation. I would like to ask the impact of other symmetry elements like roto inversions. How do you distinguish orbital from spin currents? Or they are basically momenta?
That's a really good question. So in theory, we can just calculate expectation values of different operators. But I know that experimentally it's very difficult. And as far as I know, there is not the experiment which can distinguish between spin and orbital contributions. So I think you can always compare to theoretical predictions and then maybe say, okay, orbital moment should give no sign change, spin moment gives you a sign change, and we don't see the sign change, so it should be orbitally dominated. But I think it's difficult to really have a signature just telling you about the orbital contribution. What is also done is that you look at materials with very low spin-orbit coupling. I think titanium, for example. I think there's some observation also of Hall effects where they say there should be no or almost no spin contribution. It must be orbital contribution. But I think this question about distinguishing them is a very important question in the field, which is, as far as I know, not completely answered yet.
Thank you very much. We have another question from Ryotaro Sano. Is there an experimental method? Oh yeah, that's actually this is actually related to what you just said. Sorry. So is there an experimental method to distinguish orbital magnetization from spin magnetization? And your answer was basically, well, not really.
I think there is some idea about, I mean, in XMCD, you can get like ideas about spin and orbital contributions, but I think this is usually done in equilibrium. And as far as I know, these non-equilibrium contributions are small. And I think I'm not aware about XMCD measurements on that. I've only heard it's probably too small to detect. But I'm also no expert on this method.
But I think you're raising a point because my impression is that the magneto-optical properties of a system, if you measure Mach, for example, when you measure Mach, you actually measure the orbital contribution. You never measure the spin. The spin is just a perturbation of the orbital. And, we've been using Mach to measure magnetism, but that's because of the spin-orbit coupling. If you remove spin-orbit coupling, you cannot get the magnetism through Mach. So perhaps there is something in this direction, but I agree with you. This is we have to work more. There is another question by Ningjing Yang. I noticed that the distribution of orbital angular momentum is odd in momentum space. Does this imply that the longitudinal orbital current is zero?
So this comes from the fact that you have broken inversion symmetry. And I think that the question about the longitudinal contribution is not related to the broken inversion symmetry, but it's, I think, because we have a lot of mirror symmetries in our system. But if you think about chiral materials, then you can have something like longitudinal orbital K blocking. So your orbital moments could be parallel to K or parallel to the velocity, so like perpendicular to the Fermi surface. And as long as you have, let's say, positive orbital moment at K and negative orbital moment at minus K, but both pointing in longitudinal direction, then you can also get longitudinal contribution. So this has been observed, for example, in chiral tellurium nanowires. And I think also the chiral topological semimetals are candidates for longitudinal spin and orbital transport effects.
Thank you. We have, I think, Abhijit Calais, you raised your hand.
Yeah. Am I audible?
Yes.
Yes.
Very nice presentation. Actually, you answered my second question that it's difficult to distinguish between experimentally. But can you answer that the roto inversion, like other symmetry elements, like how do you see those symmetry elements in the context of this work?
I think these symmetry properties, they are reflected in this tensor, which I always showed. So for example, here, so we define this Edelstein susceptibility tensor. which is here, for example, a 3x3 matrix because it connects two three-dimensional vectors. And so in the systems I discussed, we only have the xy and yx element of the system because we always have either rotational symmetries, mirror symmetries who forbid the other elements. But if you now think of, for example, a chiral system where you have absence of mirror symmetries, then you can have also diagonal elements of this tensor. Does this answer your question?
Yeah, I mean, we hear a lot about the breaking of inversion symmetry, but a very little literature is present about other symmetry elements like the roto inversion and the mirror plane. So I would like your opinions on the importance of these symmetry elements.
So I think if you reduce symmetries, then you can have more orientations of the induced effect. So in the systems I showed, it's really the case that, if I'm right, yeah, I think the only possibility is you apply the electric field and you get your response perpendicular to that. This is also the original Edelstein picture. But if you look at materials with lower symmetries, then you can also have like these green and purple arrows now in the direction of the electric field or maybe some direction in between. So I think the thumb rule is the lower your symmetry, the more diverse could be your tensor here. And if you look at your specific symmetry operations, then you can also tell which element is allowed and which one not.
Yeah. Thank you.
So I see that time is running, so we're going to take two last questions from experimentalists. Sachin, you raise your hand.
Yes. So thanks, Annika, for this nice talk. I'm experimentalist, pure experimentalist. So now we have these like orbital angular momentum current. So what is your opinion about these orbital angular momentum current interact with the magnetization that comes from orbital angular momentum? Because in most of the materials, we have the magnetization that comes from spin angular momentum. So if we identify some materials like some magnets, which in those magnets, the magnetization is dominated by the orbital angular momentum rather than the spin. So what is your comment on that from theory perspective?
My guess would be yes, but maybe there's something I don't consider. So it's an important point because we always say we cannot really modify the magnetization of a ferromagnet directly. We always need spin-orbit coupling because orbital current would not act at all on this magnetization. But if this magnetization is mainly orbital character, then maybe there's a choice to.
Yeah, because for example, in all like cobalt, nickel, in all these 3D ferromagnets, the magnetization comes from spin part. So what if you identify, and then we have spin exchange interaction, SD exchange interaction. So I'm thinking if we have the orbital angular momentum current and the orbital magnetization, how, yeah.
So my naive guess is yes.
Okay.
But I've never deeply thought about that.
Okay.
So maybe I'm missing an important point.
Okay. Thanks.
So we'll finish with the tough questions from another experimentalist. So Sylvain Massabo, hello, thanks for your very nice presentation. What are the main arguments to explain that theory often gives stronger orbital effects compared to spins, but experimentally these signatures remain relatively weak? That's a tough one.
So I would say it's maybe related to the detection techniques. So I think from the theory side, we can calculate these elements and we can also understand why orbital moment is larger. So some people also say, or it's established that orbital effects are the more original ones and only transferred to spin by spin-orbit coupling. But if we maybe come back to one observation of the orbital Edelstein effect, which I showed. I mean, I'm really no expert on these techniques, but what I understood here is there's a signal observed, and we know pure orbital effect should be larger, but to observe the effect, you need to get an orbital current into this two-dimensional electron gas. And this is quite difficult. If you have pummeli here, you usually pump like 94% of spin current into the interface and only 6% of orbital current. So even if the orbital effect is large, it's difficult to induce it. And I think that's just because we have this detection technique. So if you identify an orbital magnet and you can do, or pure orbital magnet, and you can do orbital current pumping, then you would probably have 94 orbital Edelstein effect and only 6 spin Edelstein effect, and then it should be dominated by the orbital signal. So I would say it's the tools we have available right now. It's my opinion on that.
Well, thank you very much for this. I think you're making really a point. So thank you very much, Annika. Thank you, everybody, for joining today. So this is the end of this seminar. Annika, you did a wonderful job. Thank you so much.
Thank you for inviting me. It was fun to speak here.
So the next the talk will be available online in the coming days, and the next presentation will be given in January, on January 16th, by Mario Cuoco on the orbital transport in superconductors. Thank you, everybody, and have a wonderful day. Annika,
Thank you.
thank you
Thank
so
you.
much, Ben, and have a great day.
Bye-bye.
Bye-bye.
Bye.